University of Maryland, and NIST. Tell us about quantum error correction.
Yeah, it's really a privilege to lecture to you all. I was a student in Boulder 7 years ago, which doesn't feel like 7 years. It's sort of a medium duration, but get to know each other. Many of you might stay and get permanent positions, academia, industry, elsewhere, and you're building this network of people that you'll know. That's what I've learned from looking back 7 years. I also learned quite a bit at the Boulder Summer School. I did the notes that year. So you're who's more condensed mattery? Who considers them more condensed mattery? Higher. Can't see you. Okay. And who's more computer sciencey? Who actually is getting a PhD in computer science? 2P. Okay. Yeah. So this is more physicsy audience. So yeah, I'm a physicist by training. I have sort of started really enjoying the computer science aspect of it, but I'm not going to do it justice. So I'm kind of like an in-between person. Nevertheless, still ask questions. I very much encourage you guys, especially this first lecture where things are just slowly starting to ramp up, and I'm trying to introduce it from the sort of computer science perspective or the communication perspective. You've all seen it a little bit in the physics perspective. So again, it's a privilege to be lecturing to you guys. And I think every one of you knows something a lot better than anybody else, including the lecturers at this point, given that you've made it here. So be confident about asking questions. There's no stupid questions. Okay. So definitely let's keep it interactive. So I'm going to do a hybrid. So when I get too lazy, I'll go to PowerPoint. Otherwise, I'll do board. What is the goal of error correction? So we all communicate using our cell phones, through Wi-Fi on our laptops. Who watches satellite TV? Anybody know what that is? Okay, so all of this involves transportation of signals and communication of signals. And if a signal is just sent out, just naked, basically like out there in the air, chances are some of it might get lost. So with satellite TV, it used to be the case that if it was rainy or cloudy, you wouldn't be able to watch satellite TV when I was growing up in the 1800s. Okay, and nowadays I hear they've made it better. I think they've changed the spectrum. They may not necessarily have made it better to use error correction or using error correction. So it's not quite the nice example I was looking for. But nowadays it's not an issue. Has anybody ran into this issue and can confirm it's not an issue? Okay, nobody watches satellite TV. Got it. Okay. But cellular communication in your cell phone, there's several different error correcting codes, which I'll get to what a code is later. But basically, there's these protocols that require you to send not just to send the signal, but in a redundant way, so that when whatever you send is received on the other end, it's possible to recover what you were saying, and your voice isn't garbled, and your email is read, etc. So the goal of error correction is to preserve messages sent through a noisy transmission channel by encoding the messages in an error correcting code. The word channel is something that, as far as I know, was started by Shannon back in the late 40s. It was this guy deserves a lot of credit because this is an extremely general framework for basically modeling the ability to communicate information. Okay, through different media, and channel here is used as synonymous with medium. Okay, and I'll show you how general it is. There's 2 points as to how general it is. It encompasses both classical and quantum information being transmitted, and it encompasses both things stuff you send through space and stuff that you're storing in time. So the parameter of the channel can be either space or time, and this Shannon theory framework still hold. The information that you're sending can be classical or quantum. The Shannon theory framework will still hold. This is 1947. This guy really nailed it. Okay. So just to appreciate, all right. So if we want to be a little bit more precise, if we want to quantify things, say the rate of corruption of this information as after we've sent it through the channel, then we want to improve this rate. So we want to make sure that the rate of corruption of the encoded, or otherwise sometimes called logical information in the quantum world, is lower than that of the same information sent without the extra encoding step. So we want to make sure that error correction works there's a notion of gain here. If this rate is lower than the unencoded rate, then you have some sort of a gain, okay? And basic error correction is all about just making sure that there's a gain. Otherwise, it's useless to do error correction. You might as well just send your signal unencoded. You want to make sure there's a gain because error correction requires a lot of work. You're going to see that there's a lot of overhead, spatial and time-wise, that goes into doing a full-blown error correcting protocol. And this is in some sense just the name of the game here. And so you want to make sure that you're doing all this work for something, okay? And I guess experimentally, it's quite interesting because now people are starting to really ramp up these experiments and are trying to see and trying to get a gain, trying to get an improvement of some rate out after putting in all this work, okay? You know, Google has this team of like 50, I don't know, they don't even say, you know, brilliant people that they've hired away from the best, you know, the best PIs and schools, and this team is hard at work trying to do a particular encoding, the surface code encoding, okay? A lot of overhead goes into this, okay? So to go back to the Shannon theory framework, so the way it works is that you have some message you want to send, okay? You want to, and I'm going to name it rho suggestively, but it can also include classical information, just to reiterate that. And to do an error correcting code, you have to encode in this redundant way. And so there's some sort of a map from your space of messages to some larger space that contains more degrees of freedom, called an encoder. Okay, I'll denote it by cal E. And then after you've encoded on your end, then you send it to Bob. You know, these computer scientists, they like the words Alice and Bob. I don't like it. Just send it through the noise channel, okay? And here, again, I want to say that this noise channel can represent transmission through space, like through an optical fiber or through free space communication, all the satellite TV stuff everybody watches, right? Or it can represent storing information in a hard drive, okay, in time. So the hard drive isn't moving, okay, and you're just storing information and coming back to it, trying to retrieve the information 5 minutes later, et cetera. So after that time has passed or the information's traveled through space, you want to extract the information back. The receiving party wants to extract the information back. In the case of space-like, it could be Bob. In this case of time-like, it's you again, or somebody else who wants to access the memory. And that's denoted by this D decoder map. The whole point here is simple, is that once you combine these maps, you want to make sure that you know, you get the message on the other end, okay? Now, I put approximate equal sign here is because, and this is especially true for quantum, we're never going to get it exactly right. Okay, in quantum, there's all these notions of fidelity and et cetera. You know, it's not going to be, it's going to be some amount of nines if you're lucky, right? So in some sense, all of error correction is approximate. Okay, the things you want to sort of try to cover with this extra mechanism is some dominant set of errors that occur the most often given your noise model, and correct those. And then maybe you'll have a small parameter, small probability with which you can tailor expand this, and then you'll have like to leading order in the probability, right? You'll be getting rho back and then plus some order probability squared or probability to some higher order corrections that'll garble a little bit your information. Okay, so any questions about this very general thing that we should appreciate Shannon for? Yeah.
There be noise before you start encoding it?
It's an idealization, right? So the noise here is exactly right. The noise here is only here. I've kind of like just compressed it all to this part, and I've assumed I have a perfect encoder, and I've assumed I have a perfect decoder. And you're right, in the real world, even that's not going to be true. And we're going to get into that. That gets a little bit into fault tolerance, namely that after you kind of understand this thing, you then, somebody asks you that question and you start to grapple with it, and you finally convince yourself that there's errors everywhere and you just have to deal with it. There's faults everywhere and you just have to tolerate them. And then that brings you to fault tolerance, where you basically have to do error correction enough so that your errors don't spread and don't become uncorrectable. So there's always going to be errors everywhere, and you want to make sure to apply this idealization to this more practical and real case in such a way that the errors that you're trying to correct don't become worse after while you're applying this protocol. So this notion of fault tolerance is something that's more trickier to me than error correction, because it requires error correction, but it also includes this interplay of how the error correction talks to all the operations and all the errors that happen inside the protocol itself. This is something more complicated. We'll get to it in the fourth lecture, I hope. Okay. But for now, let's just focus on this sort of very idealized picture where I've just kind of combined all my noise into the channel here. Anything else? Okay. And just to reiterate again, we've had about 7 years of classical error correction, from hard drives to streaming to broadcast. There's error correcting codes for all these different things. There's still there's still substantial work in classical error correction. Recently for 5G, there's big lawsuits and stuff stemming from some codes developed for I think it was cellular communication and being used in Apple devices maybe 10 years ago. So it's still more or less an active field. Much more active, I would say, well, much more sort of reinvigorated after 96 when it was created as quantum error correction, where now you're protecting quantum information. It's a much newer field. There's a little bit of a disconnect between the two fields because there's just been so much in the classical coding theory community. And so we're coming at this from the quantum side, but I want to reiterate that there's lots of important work that's been done on the classical side, and it may be useful to mine some of that work to extract some ideas from it and to port it over to the quantum side with some good results. I'm saying this from experience. Last year, I ran into some stuff that I was able to sort of port. So it's good fertile ground for research. So, right, just some historical stuff. So people didn't even think it was possible to do quantum error correction until Shor came along and just constructed a code, a close relative of which we're going to study in this lecture. Shor also showed what happened, or showed how to do a part of this error correction step that I'll show you in a fault tolerant way, and pioneered all these things in 2 years. Kitaev came along and made the connection to condensed matter almost immediately afterward, actually. And this kind of blew open 2 connections, one to physics, right? And another one that I'm hoping to briefly mention is to homology and to sort of topology, the theory of surfaces and tessellations of surfaces, with this CSS to homology dictionary. And that's been pretty instrumental in one aspect of this, this field. So yeah, he opened up 2 connections with more or less 1 or 2 papers. And both of these connections have now relatively huge, reasonably sized fields followings, working on extending them. Well, there's another paper, of course, he did that maybe is more familiar to the condensed matter community about this very nice idealized model of these the P wave electrons or S wave, I forget. P, okay. There's been several other pioneers, and as devices are ramping up and you're seeing lots of these results come out, some of you are co-authors on these papers, there's been more interest in error correction because people have started to really try to see if it can work in a real experimental device. So if you just Google things, you'll see that there's been an improvement, and this is slightly outdated. I should update it. Okay, one more sort of intro summary slide. QEC, as you've already maybe noticed, has many connections to different fields. I already mentioned the connection to condensed matter, and I already mentioned the connection to homology theory. So I just want to emphasize here that many people study QEC not necessarily to just practically realize a particular code on a particular device. They actually study it for just its abstract sort of beauty. and try to make many connections to fields they're interested in. That's in part what makes it so interesting and I think useful to really learn and understand. So I've made a list of sort of connection of different topics here. There's 6 of them, and then in the bullet point below that, I list the code IDs or the code names of example codes that I feel fall into these categories in the zoo. So you can just Google. You can Google them; they should pop up. But if they don't, go to the zoo, do the search inside the zoo, and find these codes. Okay. So the first is sort of a CSE topic. Okay, finding what's possible, developing bounds on code parameters to determine sort of the ultimate limits, the ultimate benefits you can gain with error correction, ignoring any practical restrictions, not even caring about that. Okay, just mathematically working out the ultimate parameters, and then once you have the parameters, you can try to cook up codes. Or you can have the parameters without the codes. You can derive them using entropic considerations or whatnot. But the other side of this field is actually constructing codes that try to reach the limit of what's possible in the parameter space of error correcting codes and protocols. And there's sort of codes with classical that are quantum analogs of classical codes like perfect codes, MDS codes. And then these homological product codes is what sort of grew out of the CSS to homology dictionary I mentioned by Kitaev. Many of you have heard of these quantum low density parity check codes. Who's heard of them? There was kind of an explosion of some work in them. So these are just codes with, I'll get to this, few body stabilizers for those who know what that is. Right, and feel free to look those up and read about them if you're interested. On the other end of code construction are people constructing codes for practical or near-term realization. Okay, so this is sort of this team at Google that is trying to fit the surface code to this quantum chip, to the superconducting circuit device. This is also some of you who are cooking up different fault-tolerant gadgets and codes that are intended to be realized on some device, maybe not this year, but maybe in 5 years. They're not trying to push the boundary of what's possible or reach the boundary of what's possible. They're trying to develop something that's supposed to work, that's supposed to help with some device. Okay, and it could be device specific, it could be device independent. Okay, who's got a paper on 2? Yeah, that's you. That's you. Yeah. Okay, so talk to these people if you're interested in this type of more practical, more results sort of. You see your results a little bit more here than maybe over there if it's just kind of on paper. So right, I flipped. Sorry, I split these two. So the people that are like working on with the device directly is the third category. So these are maybe theorists or experimentalists, but everything they do is trying to realize a particular code on a particular device. So I've split off this from part 2. So this is really sort of results driven. Maybe a physicist would call it engineering. And this is just a list of some of the codes that have been experimentally realized. Okay. And here come the connections. So starting from Kitaev, relating phases of quantum matter to error correcting codes. So there's some intrinsic notion of spreading of correlations and spreading of information in a many-body system, and that can be related or tied to error correction, right? That can be expressed in terms of the sort of the techniques and the tools of error correcting codes. That the state itself can be thought of as an error correcting code in some situations. The phase of matter itself can be thought of as an error correcting code. Okay, so there's very many direct connections, and so the ones you've probably heard of are these topological phases, right? And these Fracton phases, right? Who's heard of these two? Right, okay. But I also want to draw your attention to these other codes that people have been trying to prove that they're also codes out of non-topological phases, just things that satisfy ETH. Okay, and things you can write down with MPSs.
What do you mean boundary?
So yeah, encodings are some way to so a quantum error correcting code is a way to redundantly encode information and send it so that you can recover it. How well you can recover it is bounded by fundamental constraints, maybe due to entropy or due to just the size of the space you're encoding into. okay, and the level of protection that is offered by this error correcting code. These are all quantitative things that I can make quantitative later on, but just to give you a feel for it, all of these things, these quantitative parameters have some values, and so you can think of that as the parameter space of codes. So each, you can take a reasonable class of codes and you can sketch out kind of a parameter space of them, and this parameter space is bounded, and people in one, they try to reach sort of the edge of it. Like this code does the best at this particular parameter. This code saturates this bound. This code is approximately or asymptotically good, meaning the density of storage of information is the optimal, and the level of protection is also as good as you can get. So these people just head for the boundaries here, ignoring practical restrictions or limitations. Yeah. Anything else? And then there's the quantum gravity people. There's also connections between IEDS sort of CFT correspondence. I'm not an expert in this. I only know kind of something I can sketch out that's very vague, but here's some more codes that you can study for where that came from. And again, here sort of the dominant one that you're probably aware of is this holographic codes, these happy codes in particular. But I've also found a few kind of scattered ones that kind of fit into this category of like using gravity theories to try to generate good error correcting codes, or using error correcting codes to understand gravitational, et cetera, theories. And you want to check out these papers as well. Might be interesting for you if you want to go down that path. And then development of codes for sensing and metrology. Who's done that? No, yeah, one, okay. There are two codes here. I may be probably missing a few, but basically quantum sensing and quantum metrology is arguably one of the largest fields of quantum because it's the most practical. It doesn't require many body entanglement in general to do sensing. You can just do it with like a few level system. And so people in NMR, et cetera, have been thinking about doing this. And well, NMR itself is a way of doing sensing using the postulates of quantum mechanics, namely discreteness and superposition, et cetera, right? So let's say we have some signal, but it's kind of noisy, or we have some other noise in our probe, and we want to mitigate that noise. Well, this is where error correction can come in. And here, the whole name of the game is just to make sure that we can eliminate all the possible noise we can without obscuring the signal itself. Okay, so that's kind of the gist of that field. And so that actually means that you can relax this rigorous criteria for full-blown error correction that comes with a code in a way that you only need to correct, since you only need to correct the part that you can correct such that you can sense the signal. You don't need to correct everything. And so this now leads you to sort of development of codes that are intended for that purpose, not for fully protecting quantum information, but for sensing some sort of classical parameter. Okay, so that's kind of the 6 things that I could find. Maybe I'm missing something. Feel free to raise your hand and let me know, discuss. Any questions so far? Okay, so we'll get into a little bit more of the examples. So I mentioned we have our encoder, a noise channel, our message, and we want to be approximately being able to recover. So classical information the message, right, so a message row, how do you encode it in classical information? Well, your canonical choice is probably bits, right? But in general, classical information is encoded in an alphabet. And this alphabet can be binary strings, but it can also be other things. It can be query strings. It can be the reals. It can be a finite group for all you care. It doesn't, it's some set of symbols that you use to encode your information, okay? And the one we're all familiar with and I'll use over there is just a single bit, but I just want to make sure that you're aware that there's many different types of encodings here that utilize different objects here. Okay, so a single bit you can think of as just 0 and 1. You can think of it as a group under addition. You can even upgrade it to a field. What's a field? It's deeply missing in physics. I learned what a field was last January when I was talking to my classical coding theory friend. Don't laugh. You probably knew what a field was much earlier. You know what a field is? Yeah. Physics? Yeah, it's some sort of addition to operate. I don't even remember. See, no, ring is missing, right? Two operations, addition, multiplication. I think there's inverses in both, right? Yeah. Yeah. So like in physics, like people don't study this, but in coding theory, this is their bread and butter. They love fields. Okay. And so this is the primary alphabet that they use in classical coding theory. Okay. The one we would have thought they use, right? The one I thought they used was rings, which is just ZQ, the group 0, 1, ... up to Q minus 1. Under addition is a group ZQ. Who's familiar with that? Everybody, right? We love this group. Okay. But fields, yeah, in classical coding theory, they love their fields a lot more. This is a ring. It actually has fewer properties than the field. And so for classical coding theory, it's actually more useful to do fields. So anyway, so alphabets is what you encode your information in. For let's just stick to a single bit, and we can encode our message for using a single bit into our favorite quantum world by just looking at the diagonal parts of the density matrix. So in reality, I'm going to send you a single bit of information. I flip a coin, it's either heads or tails, and I want you to know on the other end, I'm going to send you the outcome, either heads or tails, right? But you don't know what it is. So you can, so the way to model sort of all the set of all possible outcomes is as a probability distribution with a prior, where the prior is some probability distribution that you kind of think my information will satisfy. Okay, and so this is sort of a way to generally understand all of the different pieces of information that I'll send you. So you know this P0 plus P1 adds up to 1. Okay, and so this is 1 bit worth of information. And so this is sort of the bare information, bare logical information without an encoding. So if I send this, what's my noise model here for this sort of normal bit type channel, binary channel? Well, it's bit flips. All right. So if I send this information just like that, then there's a chance that there will be a bit flip occurring, and here I'm modeling it by sigma x. So there's a chance that I'm going to have this process happen, and this will flip my 1 into my 0. And on the other end, I sent you tails. On the other end, you received heads. Okay, so that's corrupting the information, right? And so we want to do this more redundant encoding so that we can protect against these types of bit flips. And what's the simplest encoding you can think of? Yeah, I send you heads, heads, heads. And then this happens with some probability. Say it happened once, you're going to get heads, tails, heads. And you're going to say, well, for the most part, I got heads, so they probably had heads, right? Repetition code, right? So, yeah. So, oh, right. So the simplest way to do is repetition. Let me, yes. And let me now embed this repetition encoding, which is a classical code, into, again, our quantum world, and tell you how you store quantum information. Yeah.
You can clarify a little bit. I mean, you really are sending, what does it mean to send a text to you? I mean, you're sending a particular state, right? Like,
yeah.
You're literally sending the pulse, which is
0 or 1. That's right.
This is just statistical characterization of many pulses that you will send.
Yeah. Yeah. It's also something that is closer to heart for us, because in quantum, we're doing that as well. You know, well, I mean, with quantum, mathematically, in quantum mathematically, we're sending something that we're sampling in statistical fashion. But what's different about quantum is that that is literally a state of the system. Well, here, you're right. This is not a state of the system. This is
Does the receiver know about the statistics?
the receiver can assume something about these statistics.
I would think the error correction is maybe can harness knowledge of the probability distribution.
It's the basic mechanism does not. Yeah. Yeah, you're going down an interesting path. Like there's things with languages. You can take languages and determine sort of the probability distribution of letters in a language, and there is patterns there. Of course, it's not fully random black noise, right? White noise, but like in error correction, you're trying to preserve the whole space. So here it's a whole simplex of probabilities. Okay. Okay, so this is sort of classical. Now, if we go to quantum, what's quantum? Well, we take our alphabets here, X, and we upgrade them. So now, why are we upgrading them? We have to handle superpositions. Okay, we're not just dealing with zeros and ones. We have to handle superpositions of zeros and ones. So now we're literally sending superpositions. And so now instead of sending elements of X, we're actually dealing with functions on X. Okay, and all of these spaces have nice things that, well, that most of which are familiar to most of you. Okay, the space of functions on Z2 or F2 is just qubits. Let me show you why, just briefly. So to encoding quantum information, again, just bare quantum information involves storing superpositions of objects now, of the same objects that we were sending one at a time using pulses before. Okay. And you know what these are, right? They're complex numbers whose modulus blah, 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 squares to 1. But they're also describing or defining a function. Okay. How? Well, so let's define. This is literally a function. Okay. And these values are telling you what the function's value is at the two elements of the domain of the function. Right. This is true for all of these different things. This is sort of discussed more in the real situation where the domain is continuous, but this is also true for discrete. Okay, what we're really sending is functions, wave functions. Okay, they're called that. So this thing is really something that you can always do, and I love doing it. You can do this on a group, you can do this on some other manifold, whatever it is. This is always something that you can write down. People don't often write this down when they teach, but I hope this convinces you that we have to deal with functions now. Okay, fine. So you can also think of functions as in this nice discrete case as just a plain old vector, just a column of two numbers, right? But just more generally, you can also think of it this way, at least conceptually. Okay, and just embedding our quantum encoding or classical encoding into quantum, the only way we can do this is by basis elements. So we just upgrade each basis element into 3 copies. We can't copy the state 3 times over using a linear encoder. Homework, prove the no cloning theorem. Okay, so now here's some jargon. This is called a logical state. And these are called logical basis elements or logical code words. So this brings us to the first definition of code. A code is a subspace. It's a subspace of the larger state space that you're using for redundant encoding. A subspace is defined by what? A projection or basis elements, or some basis for the subspace. This is a basis. The code words define a basis for the subspace. Okay. The basis here is out of this 8-dimensional space is 2-dimensional. Well, it encodes a qubit. It's a 2-dimensional subspace. Okay. So now, similar to the classical case, we have this happen. And what happens now, right? So let's see. If we say have the first bit flipped, then I think I can do this in my head. We sent this information, we've encoded it, sent it through, we had this process happen. Where did we go? Yeah.
Why'd you put the data?
Because I didn't do this right in my head. Just wait till you're up here and you'll see how well you do this. Math on the fly. Okay, so what happened? We had a noise process. Where did we go? Outside of the code space. This is important. And what is something magical you can already notice? We went into another subspace, yes, but did we distort the information? Or did this information just get mapped directly, one-to-one sort of, from this vector get mapped to this one, this get mapped to this one? Our information got mapped isometrically outside of the code space, okay? And this should tell you something. So remember good old quantum mechanics? Remember this old school notion of complete set of quantum numbers? Good enough set of quantum, or good set of quantum numbers, right? What is that? There exists a set of observables that commute with each other that you can use to measure, and distinctly, once you measure them all, you can identify which eigenstate you're in uniquely. That's a good set of quantum numbers. Who's heard of this? Right? We grew up, some of us grew up learning this, right? Who's heard of this notion of complete set of quantum numbers or good set of quantum numbers? Okay, they still teach it, good. Okay, so this will help us here. What do we want to do? We want to detect and possibly correct this error. Okay, now what we need for this is not quite the good set of quantum numbers that we're all familiar with, but we need a good enough, just good enough set of quantum numbers. But before I get into that, can you already tell me if there's a way to distinguish or detect this error by distinguishing this subspace from that? Yes or no? Yeah. These states are orthogonal to these states, so there exists at least one operator observable that, say, has eigenvalue +1 here and eigenvalue -1 here. And say you measure that, you get +1, then you're there. You get -1, then you're here, assuming you started there, right? And assuming this was the noise model. So you can already detect this error, okay? And this is just something that's kind of a very bare bones thing about error correction. If your error takes you outside of the code space completely, then you can detect it. And this is true for all these other alphabets, etc., and just in general, okay? If an error takes you outside, you can detect it. Whether or not you can correct is a different story, but you can detect it, okay? We're going to use this principle, and this is, again, just basic quantum mechanics, no jargon, no nothing, okay? This is detectable. Right, but now, why am I saying we don't need a good set of quantum numbers? We need something that's good enough. Well, because we need something that can differentiate this subspace from this subspace, but we can't have something that will collapse information within this subspace or within this subspace, and thereby doing a logical measurement and corrupting or changing the logical information we're encoding. So we need something that's good enough that can resolve the inter, but not the intra, right? Between the subspaces, not within the subspace. Right? Does that make sense? Okay. And the fact that sort of this is possible was one of the major advances of error correction. Maybe it doesn't seem as wild to you now that I've just kind of framed it in this conserved or good enough whatever set of quantum numbers, but you know, this idea that you just pick them to be good enough so that you can resolve subspaces but not information within subspaces is really sort of the half the story. You can already do error detection. And we'll get into error correction now. Okay, so but how do we do this? So here comes some jargon. Lots of jargon. So we do this by doing a round or cycle of quantum error correction. What are we doing? We're trying to measure this good enough set of quantum numbers that tell us where we are. Did we have an error? Did we not have an error? And then we have to figure out what to do with that information. And this is what's called a round of error correction. So, right. So this the doing of this step, the measuring these observables, it's called error diagnosis. There's not a medical terminology. The good enough set of quantum operators are check operators. use them to check where you are, right? Then you get a set of eigenvalues, you get an error syndrome, you measure syndrome, and then you want to do a recovery. You prescribe some recovery. So, so for our repetition code, here's what happens. So I'm going to use this circuit stuff. I'm sure people have done this already before. So the 3 rails just represent the 3 physical qubits. And how do we actually do the measurements? So what are we measuring, first of all? Well, what we're doing here for this particular code is just doing majority vote. And this is sort of the quantum upgrade to majority vote. We want to measure our observables need to be such that we basically perform this majority vote. And what we do is we measure relative parities between the first and second bit and the second and third bit. So if the first and second bit are the same value, either both 0 or both 1, then their parity is 0 plus 0, 1 plus 1 is equals 0 mod 2. If they're in opposite 1, 0 or 0, 1, their parity is 1. Okay. Now that translates to eigenvalues of this operator. Okay, ZZI. You can think about that. Ask me questions if it doesn't make sense. And you'll see that this will give us, this will basically be emulating this majority vote procedure, assuming we have 1 bit flip. Right, so here's how we do the measurement. So the way I do the measurement is, this should really be C phase, sorry. But I'm trying to differentiate the 0, 1 notation with this ancilla notation by initializing these in +1, -1 states. And then I do a gate that will flip this 1 to a -1 if depending on what the state of the qubit, the first qubit is, 0, whether it's 0 or 1. And then I do that with the second qubit. And this winds up flipping it twice if the parity is 0, and flipping it once if the parity is 1. All right. And if you flip it +1 twice, you get back +1. So you don't do anything. So then when it comes time to measure this ancilla, you get +1 if the 2 states are in the same, have same mutual parity, -1 if they have different. Same thing happens for the latter 2 qubits here. So what am I getting for my syndromes? 2 binary strings, 2 bits of information. And then once I have these 2 bits of information, I need to figure out which error space am I characterizing, and then apply some sort of a correction to recover to go back to the code space. Okay, we've done this with, so we have 1 error space here that's due to this first bit flip, but now there's going to be a second, you can have a second qubit flip or a third qubit flip, right? And so we want to figure out which one happened. And we do this by cooking up what's called a lookup table. When we can do this, so we have our 2 bits of information, and then you can infer, well, if both are +1, then the first 2 were in the same state, and the second 2 were in the same state, but this one overlaps, and so all 3 were in the same state. So we must have been in the code space, because when you have 0, the same state here and the same state here, then all 3 of them are in the same state, and that's literally the code space. All 0s or all 1s. If, say, this one was a -1, then we knew the second and the third were in different states, but the first and second were in the same state. And the only way that could happen if they were in either 0, 0, 1 or 1, 1, 0. There's two options for the 3-bit binary string in both cases, because we're trying to distinguish error spaces and not information within the error spaces, right? And so there should be 2 options, and these basically determine which error space we're in. And if we say here, no, that we must be in the 0, 0, 1, 1, 1, 0 spanned error space, then we must have had the 3rd bit flipped, because we started with the code, right? Okay, any questions? Okay, so this is 1 round of error correction. I'm doing this for what's essentially classical code. However, this generalizes in relatively straightforward fashion to many of the other, almost all the other quantum codes that we'll consider that people have studied. Okay, so I'm showing the nitty-gritty details to you in this simple example, but just note that this is something that people will be doing for their error correcting codes too. If you look at papers by the surface code, on the surface code or anything else, you're going to see related diagrams and things like this. Now, one other thing, these rounds have to be performed, fast enough so that you don't have 2-bit flips happen in between rounds. This can only protect against 1-bit flip. If we had 2-bit flips, this would not give us the right correction, because if we had 2-bit flips, say the first and the second qubit flipped and the third one didn't, then we would be diagnosing this syndrome as if we flipped this one, and when we recover, we'll have a logical error. I'll speak more to that. Yeah.
This simple is a control knot.
Yeah, it flips this. Let's just define it verbally. It flips this sign condition on whether on that qubit being in the 1 state, and then the 0 doesn't do anything. Technically, this should also be 0 and 1 for this to be controlled knot. I think it's controlled phase or something. I think it's controlled phase because of the notation I'm using. It's just because I'm just not naming this to be 0 and 1. It's basically controlled knot. It's just a controlled knot. Sorry.
And just to be clear, like if you would have measured Z1, Z, so operate, check operate, then you would know the state. Like you measure ZZ1 and 1ZZ.
Yeah. Good. Good. But don't we get that for free already? What is Z1Z? Is this one times this one? And if we know the outcomes, then we multiply them when we get the third one. So we already know that, and it does not destroy the code. It's something we get for free. Right. Pairwise, right. Anything else? Yeah.
Is projection onto the voice rate applying check operator?
No. Well, it's not. It can be a Krauss operator, but it's not. It can annihilate your state if you're outside the code space. So if you're saying POVM, whether your projection inside the code space and another one where it's the projection outside the code space, is that measurement a valid measurement? Yes, that's trace preserving. It's either going to say I'm in the code space or I'm not. And that's something you can use to detect errors. Let's say you want to just detect errors. You don't care which one happens here. You just cook up a projection that just detects you being outside. Yes, you can do that. That won't tell you which error happens, so you won't be able to correct because you don't know what to do for this next step, but you can at least detect. And this is something people do in photonics. They have this code called dual rail encoding, right? Like 1, 0 plus 0, 1. And they have loss, photon loss, that takes you to the 0, 0 state, whether you lose a particle in the first or the second mode. And this loss emits a photon and you have a click, and they hear a click, and then they abort because you lost your information there. You can't correct.
Can you define check operator? What conditions are that?
I see. A check operator, I would just, my first inclination is just define it as an observable whose eigenvalues you can measure to distinguish code space. So in that sense, a projection is a valid check operator. But just wanted to make sure that you understand that you have to when you measure, you actually do a POVM, a projection operator valued measurement, where you're measuring the two eigenvalues corresponds to two projections onto the two projections onto the eigenvalues of the projectors, 0 and 1, right? And so that corresponds to actually two different projections inside the POVM on the two respective eigenvalues. You can think of a projection onto the code as an observable. Yes, if you think of it that way, then the corresponding measurement is a valid measurement. And so you can think of a projection as a check operator. Okay. I'm just so used to thinking of unitary check operators that I didn't, yeah. Exactly. So when you have a code, I said a code is a subspace. So that's great. So if you pick some crazy subspace in a many-body system, well, then what? You have to figure out how to do this whole extra overhead around it, and that is a non-trivial task for many-body systems, when everything is blowing up exponentially. Okay, and so obtaining a set of check operators that comes with a code is hard in general for general codes, and that's why we love working with specific types of codes, namely stabilizer codes, where the check operators you'll see come for free. Thanks, that was good. Definitely, yeah. Because these guys, first of all, these guys know right? They partition your Hilbert space in some particular way that's in line with what you're sending through, right? And here I've mentioned that my noise is also kind of flipping me around in this partition, but there's more general noise, and I'll show you how to handle that as well. Okay, so this is all fine and good. This is basically classical, but you can see there's a lot of stuff you can do. Now, where do we fail? Well, we fail because we're protecting superpositions, and so we have to worry about more noise than just bit flips. We can't only worry about things that change the label inside this ket. We also have to worry about things that change the relative superposition, namely phase errors. So for example, if we apply this phase error denoted by ZII, then we're going to get a sign here. There, I did that right. See? So we're getting a sign here. Okay. Now, did we leave the code space? Can we detect this error? Yes or no? No. Okay. I told you if we left, we can detect. We didn't leave. Okay. Next step. Did this error do something to our code? Did it change the information? Yes, it did. Well, we're done. This is the worst possible thing. We don't have a way of detecting this error, which would have been fine if the error didn't do anything, but it did something. It did something and we didn't know it. We're doing whatever our favorite algorithm is. Something like this happens in the middle of it. We get the wrong answer. Okay. So we have to protect against these phase errors. We don't have to do this in classical world. Classical world, we have just Hamming metric and bit flips for Hamming codes, okay, or Hamming type metric codes. But for quantum, we have to do this other type of noise. And so this noise is in some sense dual to this, right? Because now they don't commute, right? And you're always going to have this. You're always going to have some sort of bit flip noise and some sort of phase flip noise. And they're going to be dual to each other. And there's going to be Fourier involved and everything. Whatever field you pick, whatever alphabet you pick for your Hilbert space and that above the table I showed, okay? You're always going to have this. And it will always be trade-offs. How well can you do against phase? Well, you're going to suffer with bit. If you do well against bit, you suffer with phase. This is a fundamental thing. Always two types of things. If somebody tells you they only have one type of noise, they're lying. Okay. Okay. So we have to upgrade this. Okay. Otherwise, I wouldn't be giving 6 hours. You wouldn't be seeing me for 6 hours. So let's go with my first quantum code. And so again, a code is a subspace. I'm going to ignore normalization, and I'm going to give you a code that's going to detect single qubit errors. Okay, and this is what we're going to go through the rest of this lecture. And the code words are on 4 qubits. So it's a 2-dimensional subspace of a 16-dimensional space. I've arranged them in a square. These are the code words. Should be 2 things you should notice. Now, the code words themselves are superpositions of the computational basis states. Okay. Now, what is this? This is something that is required for phase noise. If you're thinking a little bit ahead, you should already see why. Well, you shouldn't, but if you do see why, well, why? Why is this required for phase noise? Yeah, tell me. I'm embedding I'm defining a 2-dimensional subspace into 4 qubits, so in a 16-dimensional space. And I'm just writing the qubits not as 0, 0, 0 in order. I'm putting them in a square because that's more compact. And I'm now defining this code by defining a subspace, and I'm pointing out that each code's basis state or code word is itself a superposition of the computational basis states of my space. And I'm saying this is required for phase error correction. Before, we had a single basis state per code word. Now we have 2 basis states per code word. And think about that as we go, why we need that. So, but let's just believe me for now, and in like 5 minutes, I'll show you why. But recognize here that if we require multiple basis states per computational basis states per code word, there has to be some entanglement. Okay, so for multi-qubit error correction against your normal local stochastic noise model, you need entanglement to protect against both bit and phase. Okay. Second thing you should notice is the Hamming weight. So what's a Hamming weight? Number of ones in a string. So there's 4 different strings here. This has Hamming weight 0, 4, 2, and 2. The logical 1 is Hamming weight 2 away from logical 0. And this helps you with the bit flip, right? Because what do bit flips do? They change the Hamming weight by 1, right? They either flip a 0 to 1 or 1 to a 0. But the Hamming weight of these guys is separated by 2. So you should already see that we're inheriting some protection against bit flips that we had here, because here the Hamming weight was also different for the 2 code words in this case. Okay. So let's get into detail of how this will be actually realized. And let's act with our code with some errors. So let's flip the first bit. So let's go back to bit flips first. And can everybody see this, or should I just write over there? If I write here, will you not see this? The what? Okay, good. Got enough space. So here we go. So again, I'm just writing this notation. I'm just writing things in like a square because I don't want to write them in a line. So we apply a bit flip. So now where have we mapped to? Well, we're going to flip this upper left corner here. Sorry, I'm already screwing it up. Okay. Okay, did we leave the code space? Yes. Can we detect this error? That should be just as a resounding yes as the first yes, right? If we leave the code space completely, we can detect this error. And I'm just going to define the basis for this error space as 0x and 1x. These are different states. There's a different space. Let's call it the x error space. So I'm just defining these states to be 0x and 1x. Great. Flipping the first bit's not the end of the story. Let's flip. We need to make sure all bit flips are detectable. Let's flip the second bit. Well, second, I mean, is the bottom left. So we flip the second bit. Okay, did we leave the code space? So we can detect it. Where do we go? Do we go somewhere else? It's different from this space, or we go to the same space? We went to the same space but we went there in a different way. Okay. Is that clear? You can, yeah, just look at it for a little bit. Maybe you didn't expect the four qubits to be this intricate, but so both errors took us to the same error space, so we can detect both at the same time. Do we know which one happened when we detect? Correct. We don't know which one happened. Do we have to worry about that? Does it matter? Does it matter which one happened? What if we just correct this error using this correction, right? How would we correct against this error? We just apply x again. We correct this error by applying this x again. What if we apply this x and we had this error happen? What happens? We switch. That's a logical bit flip. When we come back to the code, we're gonna have undergone a map that maps 0 logical to 1 logical and vice versa. That's a logical bit flip. So we can't correct these 2 errors at the same time. Why? Because they do something different within the code space when they move you into the error space. Okay, they do something within. They don't do something different to the logical information within the error space once they move you there. There, it's better. Okay, the concept or the process of having 2 errors mapped to the same error space is called degeneracy for obvious reasons. This is not something you run into in your conventional classical binary coding theory. This is something we have to live with in quantum. Unfortunately or fortunately, it's mostly a bug, kind of a feature. Okay, so get used to it. We can't just diagnose which error space we're in. We also have to know which error happened when you have two errors changing the code space in a different way. Yeah.
So that last one is what kind of error is that? It's not a phase.
This is just bit. This is just a bit flip error.
Then you said, suppose I do.
Oh, that last one.
And I correct it.
Yeah. So then you get, you're back to the code space.
Changing C0 and C1.
Exactly. It's a logical bit flip. That's called a logical bit flip.
But it feels like it's a different corruption than what you call the phase.
That's right. This is a logical phase flip. And the other one is a logical bit flip. That would happen if you had two bits flip here. Then when you do majority vote, you would exchange the two, and that would be a logical bit flip. Okay. So just to, yeah, well, you guys got it. You can detect these errors, but you can't correct them at the same time. Well, that's what I told you. I promised you this code is going to detect single qubit errors. At least I've shown so far that it detects single qubit bit flips. Okay, let's do phase flips. And here is where you want to pay attention to why I told you entanglement's important and why multiple code basis states, multiple computational basis states per code word is important. I'm going to phase flip this upper whatever qubit. Now I have a minus sign because there was a 1 here, right? Another minus sign here. Let's name these states. 0Z and 1Z. Okay. Okay, that's so far. Can we detect this error? Did we leave the code space? Right? Because state psi plus phi and psi minus phi are orthogonal states because the minus. Could I have had this if I just had one computation basis state per code word? No. That's why you need multiple, because phase errors take you more formally to a subspace in the span of the computational basis states that you've used to construct. The code itself is a uniform linear superposition with +1 coefficients. The error spaces are going to have a bunch of -1 coefficients, and you need to make sure that they're all orthogonal to even detect the error. That's why you need, for the multi-qubit case with local stochastic polynoise, that's why you need entanglement. Okay. But we're not done. We just flipped one, phase flipped one bit. Let's phase flip another one. Okay, so now there's going to be, this is going to flag a -1 when there's a 1 in the upper left corner. Right? We don't change the labels, we just do little -1 flips whenever there's a 1. Okay, can we detect this error? Yeah, where do we go? Same subspace, but in what way? This is the same state as that. This state, there's a minus sign, right? So this error mapped us to the same error space, but now it did a logical phase flip on the code. Or we did a phase flip within the error space, right? Can we correct both errors at the same time? No, because say this one happened and we pretend that one happened, we're going to have this -1 sticking around in the code space, and that'll flip C1 to -C1, right? So we can detect both errors, but we can't correct them. Okay. So far we can detect both bit and phase, right? And I'll just mention this here. I won't write it down. There's a third set we need to worry about, which is just a product of X and Z, bit phase errors. I can crank out the same kind of math here, write out the airspace, same type of behavior will happen. In the case of Y errors, you're going to have both things happen. You're going to have both the Hamming weights of the basis state labels change because there's an X component to the Y, and you're going to have some signs flip. So you're going to be going to yet another error space, 0Y, 1Y, because that space is different from the other two, the Z and the X, because it's different in both ways, in that both the Hamming weights of the computational base states and the signs. Does that make sense? So I just don't want to do it. I can do it if you want. Okay. So great. So I've sort of showed you that we can detect X, Y, and Z, and we can detect identity. That's great. But what about random errors? You have coherent noise in your device. Who's an experimentalist, actually? All right. 2 people. All right, good. So you have actual device. You have noise, right? And you're going to tell me like, this is not some digital noise that I have in my device. I have actual real noise. Everything is a pulse. Everything is continuous. My FPGA is off, whatever. But can we detect that noise or not using what you know so far? Who thinks yes? Okay. So turns out we can. And this is where the principle of collapse actually works to our advantage. And this is kind of one of these beautiful things about error correction, where something that you thought would be detrimental, namely collapse, something that collapses quantum superposition, so we don't see them in the real world, is actually going to help us now. The collapse will come from our error correction measurement, and it will take an error that's some generic error, and it will collapse it to the types of errors that we can handle. So let's consider an example of a general error. Let's consider a rotation of a single qubit around the z-axis by theta. Theta over 2, right? Because block sphere. Anyway. So, or 2 theta, whatever. What do I do with this error now? I can detect this error. Well, the reason I can detect it is because I can detect X, Y, Z, and I, and these form a basis for matrices for 2x2 matrices, right? There's 4 of them. They're linearly independent under Hilbert-Schmidt, and there's 4 entries in a 2x2 matrix. What a coincidence, right? And I can expand my operator in this basis as such. And now, when I do my check operator measurement, the check operator measurement collapses the system with respect to this coarse decomposition into error spaces and code space that I've done, that I've induced using this check operator measurement. So here is sort of a sketch of that coarse grain structure. This is a density matrix, this is a general matrix on my 16-dimensional Hilbert space. And I'm just using a basis for it where I denote the code space as the first 2 elements, then my X error space, then my Z error space, and my Y, and there's a whole bunch of other ones, right? And what do I do when I measure check operators? Well, or sorry, what do I do when what happens when this error acts on, say, the first, or this upper right qubit? Well, this error is a combination of the no error case and the Z error case. And so there's going to be a component that has the no error case, which is just up here multiplied by some cosine squared or whatever. Be a component down here multiplied by sine squared. And then there's going to be coherences between the two because we're in a pure state. These coherences are going to be in these blocks between these errors, between the code and the error space. Now here comes the cool part. When we do our check operator measurement, we drop the coherences. I wish I had the animation that dropped them. We drop these coherences and we collapse onto either this square or that square. But once we're in one of those squares, we know how to handle it, right? Then we know that we've detected either a Z error or we've detected no error. So the principle of collapse that's applied because we are doing a round of error correction helps us cut up general errors into some elements of some error basis that we've designed our code to be resilient against. Does that make sense? I don't know of many other cases where collapse really helps us. right? Like those of you who study random circuits with measurements, right? There, the intention of the measurement is to screw up the spread of correlations generally, right? But in error correcting, if you had done a measurement of like surface code or something, like a more many body check, then that actually can help you stabilize topological order, right? So measurement can obscure and stop the spread of correlations, or measurement can help in some sense. Okay. Yeah.
Can you just say again how the projection stops off?
Yeah. So when we're measuring, what are we really doing? So let's right, good. So for the Z error, we're measuring eigenvalues of this operator. And if we do, let's just restrict ourselves to this 4-dimensional space that's inside the red blocks. So if we have a +1 eigenvalue, then we're projecting onto the code space. So we have some ancillas we pull in, we do some C0s, we extract the syndrome information just enough so that we don't screw up the subspace itself. We just diagnose the subspace. We pull out, we measure, we got 2 outcomes. We got a +1. If you know the principle of collapse or Born's rule, that means you apply this projection. If you get a +1 for the ancilla outcome. If you get a -1, you're applying this projection. Right now, take the state that was there before the measurement. This is the state. I apply this thing to the logical state. I have a logical state component, and I have a component that has this error applied to the logical state. The logical state is just written like this. The error state is written like this. With a like this, right? Because I've defined my basis states this way. Okay, so I got this superposition of stuff in here and stuff in there. If I write this as a density matrix, it's like this. I apply the projection. It's either going to be in there or it's either going to be in there. That's how you kill off the coherences. Okay. The left-hand side of
The very first expression. Go down. Yeah, right there. Or that's your hard.
yeah. Thanks. I need to change. Okay. All right. So these types of projective measurements, we'll be doing them a lot. So definitely ask questions right now if you want. Okay. Yeah. Yeah. Good. When your syndromes are such that they're bits, you can wrap up your direct sum in a sort of a, when you flip this bit, you go over here, flip this one, you can make a tensor product. Yeah, you can do that with stabilizer codes. Can't always do that. You have to have this nice structure that's amenable to like changing a direct sum into like treating a direct sum as a tensor product. Anything else? Okay, good. So we've shown that we can detect single qubit bit flips. But because of degeneracy, we may or may not be able to correct them. In this case, we cannot. We've same holds for single qubit phase flips. We've shown that bit flips, phase flips, and bit phase flips, if we can detect those, we can detect single qubit errors because Pauli matrices form a matrix basis, and because measuring check operators does a collapse that actually helps us. Now, let's then go into the general case. So this brings us to sort of these QEC conditions that'll be very important for Liang's lectures as well. So please, if you've been checking email, at least try to plug in right now because it'll help you with at least Liang's lectures. So we've looked at these noise operators, which I'll just define as N1 and N2. And these, we can detect both of these. And what did this hinge on? It hinged on the fact that each error mapped the code space into orthogonal error space. This implies that a malicious environment will not be able to measure the two errors, or sorry, will not be able to distinguish the code words by measuring the two errors, measuring expectation values of the two errors. So you'll notice that, let's say, these noise operators that I've treated so far as active things that are applied by some malevolent environment that's in the channel. Now I'm going to treat them as things the environment can measure. I'll show you why I can do that in a bit. But you can indeed treat them as something that gives the environment the ability to measure. Okay. And if the environment can measure these things, then the environment can try to distinguish where you are in the code space by looking at the expectation values of the two logical states. If this one is much larger than that one, then the environment can kind of smell where you are in the code space and thereby perform a measurement or figure out where your logical information is. And if the environment can figure it out, then you don't have access to it. That's bad. Okay. So, and if these things are equal, then the environment can't smell out the difference between them. There's no imbalance, okay, in the force, and everything is good. And moreover, because the environment does not induce logical bit flips, because it takes you outside of the code space when it acts on an error, or sorry, when it acts with an error, there are no matrix elements between, or matrix elements of these noise operators that connect different code words. So these are 0. Yeah. The first line doesn't have to be 0. The expectation value can be some non-zero value. But as long as it's the same for the two code words, it doesn't matter. Right. So that comes with the idea that, look at this error. So when they're non-zero, the non-zero case happens when the error does not take you outside of the code. And I told you, if the error took you outside of the code, then you can detect it. And if it can't, then we have to worry. But what is the next question we ask? Did the error impart something logical on the code space? So look at the expectation value of Z with these two states. +1 here, -1 here. So it did something. So if you think of the error as being caused by an environment and the environment being able to extract expectation values, then it can smell the difference between the two states. While on the other hand, if you say applied this error, so read off the logical states and you do the expectation value of this error, there's 2 zeros, 2 1s, 2 zeros, 2 1s. This is just going to be +1 for both states. Okay.
The way you find it. You find it in one.
Yes. Oh, yeah. Yeah. That there, it took you outside.
Second line.
Correct. Yes. Yeah. Yeah. It's more general than topological codes. Topological order. There's lots of ways to do it, right? So this ETH code, check that one out, right? So the fact that the system satisfying ETH, few lower lying eigenstates of some Hamiltonians that are simple do this, that already can be expressed in terms of as an error detection condition, which I'm about to express this, but this it's these guys. Okay, super selection sectors, symmetry breaking, all zeros and all ones, they're protected against bit flips. Well, if you only have access to,
You're saying if I restrict.
yeah, but even, I mean, symmetry breaking, we can have discussions on this over beer, because symmetry breaking is just something that triggers me. But this super selection sector of like this guy, you can't smell this guy out. All zeros and all ones outer product. Like there's no operator, no local operator to connect this to that. So this can be there, this cannot be there. I don't know, maybe you guys know much more about this. But philosophically, is this all ever there? Are we in a superposition of super selection sectors, or have we collapsed to one? We can't tell, right? Isn't that so that's also a manifestation that can be expressed in terms of error correction condition. So it's the LDPC codes are not geometrically local few body systems, but they also satisfy this for some distance for some operators that are weight up to order 1 or even more. Okay, you don't have to be just topological. This is more general, yeah. Yeah, TQ01, TQ02 is a necessary. What is a necessary condition? Being a quantum code is a necessary condition for topological order. So, but being right. So if you have topological order, then you are a quantum code. Then you satisfy these things for operators that are local, geometrically local, given your geometry. But not all quantum codes have to be topologically ordered. The converse is not true. Okay. And we got an expert in that stuff over there. So, yeah.
Question maybe a little bit ill-defined because I think one of the check operators
Yeah.
is completely non-local.
Yeah.
If you write this as a Hamiltonian, it's completely non-local.
Yeah.
I don't know what local stability.
Yeah, and you shouldn't, given everything I've lectured on so far. I'm borrowing here on other people's experience. The system is 4 qubits. Yeah, but we'll scale this code up to more, and Alex will talk about stuff. So, okay, so let me just express this in a more concise way as the quantum error detection conditions. So I'm going to define, I already defined actually the projection on the code space. So it's up there, right? See it? So we're going to use that, and we're going to combine these into one. And we're going to say that we can detect a set of errors if for all element of the set, some set n, we can project the error into the code space and get back the identity on the code space with some coefficient, which may or may not be 0. This has to do with what I thought Leo's question was. Okay, so project the noise into the code space and get identity map. Now, when is this coefficient 0? And this was related to your question. When you have bit flip error, the support of the error space that's obtained by applying this to this is orthogonal to the code space because we've detected them, right? So this coefficient is 0 for that case. But this coefficient need not be 0. For example, here, right, I've shown you an operator, ZZII, where projecting ZZII into the code space gives you something, but it gives you something trivial. It gives you the identity map on the code space, namely, also known as the projector on the code space. Gives you +1 here times the projector on the code space. Also perfectly kosher, right? Because we didn't leave into a detect, we can't detect this error, but we don't need to because the error didn't do anything, right? And had the error done something, then we would have this plus some other thing that would be bad. We're not satisfying the quantum error detection conditions, we can't detect that error. So there's maybe a convolution of language here. This is error detection, so you say you can detect this error. Well, when the error doesn't take you outside of the code space, but also doesn't do anything, you're detecting it as the identity error, which is sort of saying no error, but depending on who's talking, detecting identity error and no error happening is kind of the same. But linguistically, maybe it's a little bit confusing at first. Okay. Now, let's do now the quantum error correction conditions. So now I mentioned that you have, yeah. Okay, let's just do the error correction conditions then. So we had two errors that took you to the same error space, and but we had them do different things. And so when you use one to undo the other, we failed. And why would we use one to undo the other? Because we have to pick a recovery operation. We don't know which one to pick. We have to pick one. So just to reiterate that, let's say we had N2 happen, and we left into the error space, but then we maybe think N1 happened, and we undo it using N1's operation. We don't need dagger. Well, we need dagger, but in this case we don't. In general, we do. And then we see that we remember that N1 has taken us to this other case. Well, and I can show it to you. So these two errors, just writing them together, give you this. And looking at what this does to the two code words at the bottom left board there, right? Just stare at that for a bit. Two. Okay. So we combine them, we get this. What happens with logical 0 when this is applied to it? We get 1. Logical 1, otherwise known as 1. Otherwise known as not 0, right? We've done a logical bit flip by first having an error happen and then using a recovery that was wrong for that error. This is a violation of the error correction conditions. And the error correction conditions basically say that we need to make sure that if we have an error that two errors that map us to the same error space, they better be able to undo each other, because otherwise we can't correct for both. At least that's one way to think about it. And we can write these in a very nice, concise way as well for any errors pairs nj and k. Please raise your hand if some writing is off. My 2s are going to start looking like alphas. If we project the product of these inside the code space, then we better get identity. Okay? Namely, this one better be able to undo the effect of this one. Now, this is something that we have to worry about only when they take you to the same error space, right? If the errors map you to different error spaces, if all the errors map you to a distinct error space, you're not degenerate as a code with respect to that noise model, then we have to worry about the weird non-zero C coefficient, because they all take you to a distinct error space. So you have enough syndromes to resolve all the error spaces, or resolve all the errors. You don't have to worry about conflicts of errors. So they all are correctable if they're detectable. But if you have them mapped to the same space, then they better be able to undo each other. And the undoing condition can be described like this. That's the error correction conditions. Okay. Yeah, so that's probably a good place to stop.